Hello, everybody. Go on in. Hey, Sing, how you doing? Looks like just two of you so far. Anybody have any questions while we're waiting for them? Sang or Julia?
Okay. Can you hear me?
Yes, I can now.
Hmm.
I don't think I'm going to win any Room Raider awards with this background. Oh, I just noticed one of the boxes says Fireball on the side.
Did your friend finish the construction job?
Yes. Yes, and we're still
Okay.
working on, well, I should say he finished one of them. Now I have to do the rest myself now, so yay.
Uh,
But
you
yeah, we
said you said you were building the bookshelf, right?
yeah, and that's basically what all this is sitting on right now is the bookshelves are there. I haven't put the shelves up yet because I still have to paint them. But the other side over there, he didn't do that at all. So I still got all those books now. And that side on the other side of the house is my library. This one's my office. So my office
Mm.
cabinets are done, sort of. Like I said, I need to paint them, and then we got to do the trim work around it and that sort of stuff. But I don't know when he's going to show up again.
Okay.
It's hard to find good, helpful workers that will show up every day. Hmm. Well, I guess it's time to start class. It's not really the best case scenario with only three people. All right, we got another one in here. Woo! Now we got four people in. So we got to do a little catch up. I did manage to find that quote I told you guys about, which I think I told you about. Actually, I might not have even got to it because it was I didn't get to talk too much about the molecular structure of matter and how basically the atomic theory of matter is so important. So I did put up in week one, you'll see Feynman quote underscore atoms, and that's the direct quote, and it actually has a link to where it came from, which is in his book, the Feynman Lectures on Physics. So you have that now. And that's basically what we're supposed to be starting with in chapter 17 is using basically the atomic theory of matter. So I talked to everybody about the atomic theory of matter being basically introduced by Democritus. I said I thought it was in the 200, 300s BCE. I'm not that certain about the date, and I didn't bother to double check it. But the main important thing is it was a long time ago. And his reasoning was, like I said, you could either split something in half forever, and it seemed much more reasonable to Democritus that you couldn't, uh, or you couldn't, and then that smallest thing that you reach is the smallest thing that is really that particular material. So in modern language, we basically interpret that to be if you actually are dealing with an element, which is one of those things that are on the periodic table, hydrogen, helium, lithium, beryllium, boron, carbon, oxygen, and so on and so forth. If you happen to be dealing with one of those substances, then yeah, you keep cutting it out down, and you get what we call, with a modern word, of atom. Again, the word atom being atom, which means indivisible in Greek. But in that sense, in that Greek sense, is not really that true, because we can cut the atom in half. We can, in fact, break the atom apart. And it's actually quite easy. In fact, we do it to some extent. We're just rubbing our feet on the carpet, because we're actually stripping electrons off of either the carpet or your shoes in that case. So that's sort of the modern versus the original definition of an atom. But what we also know is if we do that with a compound as opposed to an element, so these are two or more different molecules of the same element that are, excuse me, two or more molecules, one of one element and another one of another element or more, then you get what's called a compound. And that compound, if you take that sample of that compound and you cut it in half, and then you take one of the halves and you cut it in half, and so on and so forth, again, like Democritus imagined, there is a smallest part at which it's, if you break it apart, it no longer behaves like that compound. So the elements like iron, for instance, if you cut that in half and then cut that in half and then cut that in half and keep on going, it will go until you get to the smallest part that's left, and that still has the properties of iron, and that thing is an atom. But when you do it with a compound, that thing is a molecule, and then when you break the molecule apart, then it acts like the constituent molecules, is constituent atoms of the molecule. So for instance, a grain of salt cut in half, cut in half, cut in half would eventually reach the smallest part that still behaves like salt, and that would be a salt molecule, which is one sodium and one chloride, chlorine atom bonded together. If you break that apart, then one will act like sodium and the other one will act like chlorine. So we're back to the actual atoms idea. So Feynman really thought that was fairly important, and I'll read the quote now that I actually have it listed on your week 1 module. So I'm going to go ahead into that. And basically what Feynman said was, if in some cataclysm all of scientific knowledge were to be destroyed and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, or the atomic fact, or whatever you wish to call it, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squished into one another. In that one sentence, you will see there is an enormous amount of information about the world, if just a little imagination and thinking are applied. So that's by Richard P. Feynman from his section on atoms in motion in Feynman Lectures. And if you look at that document, there's a link to that particular page of the Feynman Lectures. So anyways, that's sort of what we're doing here now, as we're trying to point out to you the importance of the atomic idea, or the idea of the atom. So with these little atoms, we do know that they jiggle around sort of in perpetual motion. In fact, what we've now determined is that at least that translational motion of those atoms, the actual atoms moving decidedly in the forward direction, or decidedly in the left-right direction, or decidedly in the up-down direction, those motions have associated with it an average kinetic energy, and that average kinetic energy is literally just a constant away from being the absolute temperature in Kelvin. So as you get down to 0 Kelvin, obviously that motion would slow down, slow down, slow down. But we find it doesn't actually go to 0. So in that sense, it breaks apart. And that's what we call the 0-point energy. But still, we can run with that model and think, okay, what happens with atoms and molecules? So atoms and molecules are made up of charged particles. We know, for instance, that the nucleus is made up of protons and neutrons, or in the case of hydrogen 1, it's just a single proton. That proton is positively charged, and then orbiting that proton, in some sense, is the electron, or the electrons. In general, a neutral atom will have just as many electrons as it does protons. But what we find out is the force of attraction between the proton and the electron is not gravitational, even though gravitational does actually act. That thing is like about 1 with 40 some zeros after it times smaller. So evidently Alexis is listening to me trying to answer something. But anyways, that idea that the individual atoms are made up of these charged particles and that it's not gravity holding them together, but rather this electric force called the Coulomb force. And the fact that the Coulomb force is so much stronger than the gravitational force tells us that we need not worry about the gravitational force when we're dealing with atoms in general, just because they're not going to be an appreciable fraction of a force compared to all the other forces. But that force will, in fact, cause, for instance, when one atom gets near another, it'll be two negatively charged electron shells sort of near each other. That's going to compel the electrons to try to run away, and one will run away a little more efficiently than the other, and therefore that particular atom will become polarized, and that particular atom will have an affinity for the other atom because now they're somewhat acting as if one's positively charged and one's negatively charged, and they can't even share the individual electron. And it turns out that there's a finite distance between the individual atoms where equilibrium is established. And of course, the higher the temperature gets, the faster that motion is, and therefore the equilibrium changes. And you get the idea that the equilibrium with faster and faster random motion is actually going to get farther and farther apart. And that tells us, for instance, that matter should probably expand as temperature increases. And that's generally exactly what matter does. There are some very specific cases where it doesn't do exactly that, water being one of the most amazing ones and one of the most helpful ones for us, because without that particular fact in nature, life probably wouldn't have been able to exist through some of the ice ages we've experienced in the past. But because water does, in fact, expand upon increasing temperature up to a point, we find that, in fact, the maximum density of water, which is the mass per unit volume, occurs at 4 degrees Celsius. So if you get any hotter than 4 degrees Celsius, the water becomes less dense. In other words, the atoms get farther apart. But also, if you get colder than 4 degrees Celsius, the atoms get farther apart as well. So that's an anomalous behavior that your book talks about. But if you continue that idea, you get the idea that it's going to slowly move further and further apart. And in fact, in the solid state, the individual atoms form what we call a sort of a lattice. And some of them are very precise about how they get in the lattice. Other ones, not so much. But the main thing is you can sort of imagine like here's an atom, which, by the way, I could be talking about molecules too if I'm dealing with compounds. So just keep that in mind, but I'll keep saying atoms. But you have an atom here and you have an atom here, and then there's another atom up here, and then there's another atom up there, and then there's another row of these atoms right behind it, and then in front of it, and then there's more on this side, more on that side. So you get sort of a rectangular grid, if you will, of atoms, and that's really the lattice that makes up a solid. But as I said, as the temperature gets hotter and hotter, or higher and higher, the jiggle gets faster and faster, and the equilibrium position gets further and further apart, till eventually what's going to happen is the equilibrium position is going to get so big that it really makes the intermolecular or interatomic forces, the forces attracting one atom to the other, or the forces attracting one molecule to the other, to become so weak that they sort of break their tether. Not completely, but they break their tether in the sense that this atom is no longer going to be right next to this atom and this atom and this atom and this atom. It can actually break loose and stay maybe around one of those for a little period of time, but it's somewhat free to move. Once you supply that last bit of energy that's needed to break that bond, that energy is called a latent heat of fusion. Then the atoms sort of act like, our molecules sort of act like they're rolling around on top of each other, only it's like their size is so much bigger because they're so less densely packed. But they're no longer in that rigid lattice structure. And that's what we see with solids. If you take a solid, you lay it on a table, you come back, it doesn't change its shape, nor does it change its volume. Well, guess what? When you go and break up that lattice, now you've got the atoms and molecules that are free to roll over top of each other and stuff like that, and they're still jiggling. So as temperature goes up, they jiggle a little bit faster. So the proximity of one to the other as it's sort of rolling around one another does actually change. So they get further and further apart. So the liquid does in fact expand upon being heated up, and we'll talk about that as well. We'll see, for instance, that gasoline as a liquid actually expands quite a bit compared to, say, steel. But that's a typical case. So we're now in the liquid state. These atoms or molecules are free to roll around each other. So that means, hey, if you take, let's say, an ice cube and you lay it on the table, and then you wait for it to melt, it will eventually melt. And when it does, that's becoming basically a liquid. At that point, it's still a fixed volume. It's a new fixed volume from what it was when it was solid, but it's a fixed volume, and that's not going to change. But the shape is pretty much whatever container you put it in. So if you leave it on the surface of a flat table, then it's going to form sort of a bubble due to surface tension, but it's going to maybe take a roundish shape, or if it happens to be laying in a circular-ish divot, then it's going to be circular. If it happens to be in a square divot, it's going to be square shaped in some sense, and so on and so forth. So that's the classic principle of a liquid. It has a definite volume, but not a definite shape. Now, if you continue to heat it up, of course, that jiggling gets faster and faster and faster. As we said, the modern definition of temperature being the average kinetic energy of the translational motion of the atoms or molecules in the substance. Literally, it's just a single number times that you could say gives you the temperature in Kelvin. But as that temperature gets hotter and hotter, eventually or higher and higher, eventually what's going to happen is even those bonds that keep maybe this atom really close to this atom for a long period of time, which might literally be only microseconds, but that's pretty long time compared to how they move. It'll eventually roll over and get to another one, so on and so forth. But eventually it'll get so hot, and an extra amount of energy will finally be put in to break that last bit of molecular or atomic bonds between one atom and the next. And then the things are free to move, and they're going to go quite a big distance compared to their diameters away from each other. At that point, we've transitioned from a liquid to a gas. And of course, as you continue to heat that up, the atoms become faster and faster. That causes a higher and higher pressure. So you see pressure and temperature are directly related. So you can get all this interesting information just from reasonably thinking about and imagining a scenario with little balls moving and vibrating and stuff like that. And that's what I think Feynman was trying to let us know with that quote in his lectures on physics. So that's why we actually started off with chapter 17 talking about that. So one of the things we have to realize is we're going to look back at the periodic table with a little bit more knowledge. We're going to take, instead of thinking about the periodic table like we did in chemistry, where you had a column on the left-hand side, and that column would represent, for instance, hydrogen at the top and then lithium right below it and stuff like that. We know from chemistry that any of those elements in that same column really behave chemically similarly. So hydrogen and lithium both sort of behave the same. And again, whatever's below that will behave the same way, as so on and so forth. And then if you go over to the next column, then that's the column that often helium's in, but they'll usually put helium there, and then they'll put it at the other side as well. Because it behaves really like both of those period 2 elements, or those second column elements, as well as that last 8th column element. The last 8th column element being what we call the noble gases. And they're sort of like snobby in that they tend not to bond with anything. Okay. Well, that's also what these period 2, in other words, column 2 atoms do, because they actually end on an s orbital, and the s orbital only holds 2 valence electrons, and it's got both the valence electrons full. Okay, so they don't really necessarily like bonding. They're a little easier to, because it's an s orbital as opposed to a p or a d orbital, but still the main point is those things have a closed or a full outer shell. And then each of the other ones is a progressively more electrons in the outer shell, working up again from 1 to 8, 8 being the last number that you run into on the, I'm pretty sure it's 8, but anyways, up to the noble gases. Now, that's a very interesting thing, specifically because if you look at anything in column 1, which includes hydrogen, basically the bonds that hydrogen makes, the things below hydrogen can do sort of the same thing. So H2O is water. Well, guess what? There's also Li2O, which would be lithium, dilithium oxide, which is not necessarily like water, but it bonded like hydrogen did in water. So that's kind of neat. We also see things like, for instance, if you look at calcium in the bones actually is very relevant to the human body. And below calcium is an element called radium that Madame Curie discovered. And when we first discovered it, we didn't know, we knew it was radioactive, or we might not have had a word for it at that time, but a word came shortly thereafter. But we knew it put off energy. You could see, for instance, it would develop film on its own with no light and stuff of that sort. But a lot of people really weren't sure that it was dangerous. Poor Madame Curie and ended up dying of some pretty rough cancer from working with it so much. But it's actually even more tragic of a story, not because one person's life is more valuable than another, but specifically this is around the early 1900s when the men in America, at least, were away at World War I. And what we discovered with this radium is that this element was really cool because you could like put it on something, smear it on something, and shine light on it, and then take the light away and it would glow. So they started putting it on watch faces to illuminate the numbers so that you could then see your watch even at nighttime without a light. And that was a good thing. So they put people to work doing that, and they would have these young women, again, because the men were at war, young women would take and paint the radium onto the individual watch faces. And what do you do when your little paintbrush doesn't make a fine point anymore? You stick it on your tongue and sort of caress it into a point. The problem is they didn't know radium was dangerous, so they were doing that and actually ingesting it. And then they had this rash of 23, 24, 25-year-olds having broken bones like they were 90 something, because what had happened is because of the chemical similarities between calcium and radium being in the same column in the periodic table, the body was interpreting the radium to be calcium and sending it to the bones. But the radium's not good like calcium in that it doesn't make strong bone bonds, and therefore the bones would become brittle and break, and the women would even literally glow. So it was a really a horrible tragedy, but it happened in a lot of different ways because a lot of people just didn't know that it was deadly. One case, for instance, was if you walk into an old shoe store, for instance, they had this brand of shoe that I always thought was like the best of the best, but I think it's sort of like the poor person's nice shoe, and they're called Florsheims, and they had Florsheim machines, and the Florsheim machine would be basically you could stick your feet in it, and an X-ray would shoot straight from under your feet right towards your gonads, which I point out on purpose because if you look up in the CRC, for instance, and look at what the maximum limits of radiation exposure are, they'll tell you 5,000 rems per year at the gonads, because the gonads are the most sensitive. So as you can imagine, they're shooting X-rays directly at the gonads, and the result is you get to see the X-ray of your feet with a little drawing of different size shoes imposed upon it, so you can sort of guess what size shoe you're going to wear based on the X-ray of your feet. But again, they didn't know it was deadly. A guy by the name of Elihu Thompson wanted to convince everybody that it was in fact safe, so he decided to hold an X-ray tube against his finger for, I think it was on the order of minutes every day. And he's really quite braggadocious at various points, saying, as I told you, it's as natural as the wind-driven snow and stuff like that. 5,000 millirem. Yeah, thank you. It's 5,000 millirem or 5,000 rem. I misspoke. Excellent. How did you know that, Taylor? That was excellent. It won't let you type rem for nothing, will it? But yeah, it's 5,000. It's 5,000 millirem or 5 rem. And in the case of X-rays, photon radiation, rem is the same thing as a rad, so that helps as well. But yes, I'm sorry, I misspoke on that. So, anyways, these Florsheim machines would actually be used to do that, and Elihu Thompson was going to show everybody that it's not dangerous. But you finally look at his notes as he's keeping them, and it's like, he says, my finger is a festering boil and it smells like putrid flesh. And then like 2 years later, my finger is only now beginning to heal. So he determined that, in fact, it was dangerous. And and thank goodness for us, because we don't just randomly let people get x-rays anytime they want anymore. So yeah, there's a lot of bad things that sometimes happen because we just don't know stuff when we first introduce something, and radioactivity was one of those. Even when we first knew it, we didn't necessarily know that it was coming from the nucleus. But people like Madame Curie, who's one of the only people, by the way, that won 2 Nobel Prizes. I think she is the only one. She won a Nobel Prize in chemistry and a Nobel Prize in physics, which is pretty impressive. And she shared the Nobel Prize with her husband on the first case. I think the second case was all her. So she was friggin' the man, or excuse me, the woman. So anyways, so back to the ideas of atoms and the periodic table. So just remember that idea of the periodic table has this wonderful structure that Mendeleev found, and it was specifically how the properties of the material played out. And it was just the most beautiful thing that could come together. And not only that, if you notice, it's got the atomic number of 1 for hydrogen, and 2 for helium, and 3 for lithium, and 4 for beryllium, and so on and so forth. So if you go up all the way up to 100, 116, or whatever we're at now with some of the theoretical things we've discovered, you'll notice that is, there's no holes, there's no elements missing. And that's why we're 100% confident that we will never find some element between hydrogen and nitrogen, or something like, well, I shouldn't say hydrogen, maybe between oxygen and nitrogen. Okay, because it's really just counting, because it turns out that atomic number is really just the number of protons, and that's what dictates how the atom bonds, because the number of protons in the nucleus dictates the quantum mechanical structure of the atom and how the electrons bond. And the way that the electrons bond is what actually causes atoms to bond with other atoms to make molecules. So we're never going to find, a 3.5 proton atoms, because there's only, whole protons. So we're not going to do that. Now, there might be islands of stability out past 116 or something like that, but we just don't know. Okay, I think there are some ideas about there not being any islands of stability, but in principle, there might be. Who knows? Okay. The other thing about the periodic table is you look up there and it'll say hydrogen 1.007944 or something like that. I'm not looking at a periodic table. I'm just pulling stuff out of my memory, which may or may not be that good. And I think that one seems kind of correct. And then helium has another mass, and it's 2 point something something. And then lithium has another mass, and it's like 3 point something, so on and so forth. That mass, at least from your chemistry class, you tend to think of it as a mass in grams per mole, where mole is a quantity of substance. And what we mean by that is, specifically, there exists a number called Avogados number, which is about 6.022 times 10 to the 23rd, meaning we really don't know. I don't think we know all 23 digits, but basically the number is 6 followed by 23 digits. And we know the first 3 at least are 022. And actually, if you look in the front cover of your book, at least in the hard copy version, it shows you a large number of digits that we have. I think it's on the order of maybe 8 digits that we actually have, but the rest of the digits we don't know that well, as far as I know. So that's Avogadro's number, and that's the number of atoms in a mole, and a mole of anything. So for instance, if you talk about a mole of water, then you're talking about that number of molecules. Or you could even talk about a mole of nails, in which case you'd have 6.022 times 10 to the 23rd nails. So really that's all that matters, is it's a number. So that's the way we think of the periodic table in terms of those masses. And in fact, they're a little different. I'll tell you that the gram per mole is true and it continues to work, but it's also sort of not true, in that those numbers are actually what we call weighted averages. Remember, I told you guys about making sure you know how to do weighted averages so that you can calculate your own grades and your own GPAs and stuff like that. Well, what we've discovered is that hydrogen is not just hydrogen. Hydrogen has sort of other flavors, if you will. So hydrogen that we run into day in and day out is basically a proton with an electron orbiting around it. And actually, on planet Earth, it's mostly H2. So it's actually molecular hydrogen, where two hydrogens bond together because both of them are deficient one electron. So they can share sort of one electron between them. And they're much happier as a molecule of two hydrogen atoms than they are a single atom. But the main thing is that's not what I'm talking about. The different flavors of hydrogen include hydrogen 1, which is basically a proton in the nucleus, and the electrons don't really matter too much in this discussion. Then there's a hydrogen 2, which we call deuterium, and that one is basically a hydrogen that has a proton and one neutron in the nucleus. And then there's tritium, which is hydrogen 3, which has a proton and two neutrons in it. So just about essentially every element has those flavors, and those flavors are called isotopes. It just basically means that they still behave chemically exactly like hydrogen 1, hydrogen 2, hydrogen 3. In other words, hydrogen 1, 2, and 3 behave chemically the same way, but they are definitely heavier because neutron's about the same mass as a proton. And remember, the proton's over 1,000 times heavier than the electron. So it's the lion's share of the mass anyways. It's like, 1,250 times the mass of the electron. So these different flavors have different masses. And because of that, what they've done on the periodic table is they say, well, how much hydrogen 1 exists? And they'll say, oh, it's 99.96% or something like that. And say, okay, well, how much hydrogen 2 exists? And that's like 0.024% or something. And then hydrogen 3 is 0.0034. So what they do is they multiply that percentage, the 99.96, and I'm making those numbers up. I have no idea that they're that. But you take that 99.96%, convert it to a decimal, multiply that by the mass of the hydrogen 1 atom, and then you take the percent for the hydrogen 2, convert that to a decimal, multiply that by the mass of the hydrogen 2, and do the same thing with hydrogen 3 and any other isotopes you'd have. And then when you're all done with all the different isotopes, you add all those individual products up, and then you divide it by the sum of all those percentages. And of course, if you really covered all of them, the sum of those percentages would be 100% or just 1. That's the weight that we see on the periodic table. So that'll become relevant in a second, because what I'm going to tell you is there is in fact another weight or another mass that corresponds to that number that you see on the periodic table. And that number that you see on the periodic table can be expressed as atomic mass units. So if you say hydrogen is 1.007244 or something, then what it means is, yeah, that's 1.00724 grams per mole, but it also happens to be 1.00724 atomic mass units, which is the mass of the hydrogen 1 or actually it's the combined mass of all the isotopes in a weighted way. But the main thing is the atomic mass unit is 1.6605 times 10 to the negative 27th kilograms. So it's a very, very small mass quantity. Well, I say very small. It's very small compared to everyday life, but it's comparable to the mass of a proton, but way bigger, for instance, than the mass of an electron, which is like 9.109 times 10 to the negative 31st kilograms. So that's the new way of doing it. In other words, that's a new version of what those masses mean. And it was based on the idea of, hey, let's find a unit that's really helpful to talk about the mass of atoms. So that's where the atomic mass unit, which is just abbreviated with a U, that's where that came from. And they based it on the idea that carbon-12 would weigh exactly 12. Okay, so carbon-12, which means it has 6 protons and 6 neutrons, because carbon has the atomic number 6, so it has to have 6 protons. But since it's carbon-12, that means the total number of protons and neutrons is 12, so it's 6 and 6. So they just defined that as the standard and said that would be exactly 12.000 to an infinite number of decimal places atomic mass units. So if you think about it, it's 12.000 U atomic mass units. And it's also 12.00, again, for the carbon-12, 12.000 grams per mole of carbon-12. So you might realize that, wait a second, if I'm talking about mass per atom, then that 12.000 grams per mole is Avogadros number times the mass of the atom. So you'd actually figure out that the atomic mass unit is literally 1 over Avogadros number. So you can take your calculator right now and do 1 divided by 6.022 times 10 to the negative 23rd, and you'll get something that looks a lot like atomic mass unit. It'll come out to 1.6605, say, but the exponent won't be right. The exponent will not be 10 to the negative 27th. That's because that's in grams. So you got to move the decimal 3 places to get it to kilograms, and then lo and behold, you have exactly the atomic mass unit. Okay. So that's kind of neat, and that's a new version. And now that we have that, we can actually do neat calculations. So I'm going to take the time to share my iPad screen with you guys. So I'm going to hit share screen. I'm going to do iPhone, iPad via AirPlay, blah, blah, blah. And now I'm going to select screen mirroring on my iPad. Screen mirroring. Harder to say than you might think. Okay, so I've got it coming up. It might take a couple seconds, but you will see it. And it would be really nice to have a periodic table right now, but I didn't bring the book with me, so we'll just deal with it. Not a big deal. Okay, so what we found is that Avogadros number N sub A is about 6.022 times 10 to the 23rd. And it normally states, if you have a book or something that this is tabulated in, it'll normally state moles to the -1. And that's because it's really somethings per mole. So if you're talking about a mole of frogs, it's frogs per mole. If you're talking about matter, then it's atoms per mole. If they're elements, or if you're talking about compounds, then it's molecules per mole. So that's really what that is. And what I'm telling you is the atomic mass unit U is supposed to be about 1.6605 times 10 to the negative 27 kilograms. So if I take my calculator and do 1 over Avogadros number, I'm going to do that right now. 1 divided by 6.022 e to the negative 20, or e to the positive 23, excuse me. And that gives me 1.66057788 times 10 to the negative 24. And remember, that's moles per gram, basically. So that's, or excuse me, grams per mole, basically. So you're now in grams, not kilograms. So if you convert that to kilograms, then it'd be 1.6605 ... all those digits times 10 to the negative 27 kilograms, which is what we got up there. The main thing is I only use 4 sig figs. So 1, 2, 3, 4. All of these are not really justified being anywhere near correct because I only put in 4 sig figs. Now, the good news is if you put in 8 sig figs, then it'll match the U value to 8 sig figs. So now that I've established that for you guys, and we've got some sense of how matter behaves as a result of these atoms that are jiggling all over the place, we can actually solve a problem. So the problem is, let's say, example. So here's the example, and it's going to be how far apart are the atoms in a copper block at 20.0 degrees Celsius. So right now that seems like virtually impenetrable problem because we've got no information. But what I will tell you is I know that the density of copper at 20.0 degrees Celsius is about 8.9 times 10 to the third kilograms per cubic meter. And I know that the molecular weight of copper is in fact about 63 atomic mass units. And actually, I'm using it for specifically like a single isotope of copper. If you actually look up the atomic mass of copper, it's like 63.546 or something like that. But I'm only using 2 sig figs, and I'm not really caring about it being rounded up. So I'm just going to call it 63. Happens to be the same numbers that your book used. So that works out okay. So let me show you the process. There's no formula I'm going to give you, or no formula we're necessarily going to derive to calculate this, but I'm going to use dimensional analysis and just clean reasoning and thought to come up with the separation distance between them. So let's imagine, in fact, that we have a block. Notice the density says it's 8.9 times 10 to the third kilograms. That's literally 8,900 kilograms in a cubic meter of copper. So we can actually picture, I want to say solution. We can actually picture a 1 meter by 1 meter by 1 meter cube of copper, like so. This would be 1 meter wide, this would be 1 meter deep, and this would be 1 meter tall. And not only that, I'm going to imagine it as if I've got in that lattice structure we're talking about, I'm going to have one atom, another atom, another atom, another atom, dot, 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 all the way up to here, such that this is going to be in atoms lined up on that row. This side's going to be dot, dot, dot again here. So this one will be in atoms as well. And then finally, this one back here, dot, 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 dot. This is going to be in atoms as well. So what we have is that n times n times n equals n cubed equals the number of atoms in the 1 cubic meter cube. Okay, so we can think about that. Now, if we're going to say that the number of atoms in the cube is n cubed, and we know the total weight of the individual, or excuse me, of the total sum of all those atoms, and we also know the weight of a single atom, then we can figure out what that number of atoms is by multiplying that number of atoms times the weight per atom. So what I'm going to do is I'm going to say n cubed is equal to, of course, 63 u, which or let's put it this way. I don't want to say equals, because n cubed is just a number, and if I said equals, it wouldn't actually be true, because I can't have the number of atoms equal to the mass of the atoms, because they're entirely different quantities. So I'll just say n cubed implies that 63u, which is equal to 63 times 1.6605 times 10 to the negative 27 kilograms is equal to the mass of a copper atom. So doing that, I see that the mass of the copper atom is in fact equal to 63 times 1.6605 times 10 to the negative 27th. Thank you. And that gives me, actually, I need to write it somewhere else because I've used up too much space. So I'm going to say M copper atom is equal to 1.0461 times 10 to the negative 25th kilograms. Okay. Now I only had 2 sig figs to work with. So technically speaking, this, and this digit are not sig figs, but I'll just keep them because you always want to keep at least one more extra sig fig when you're doing calculations with a number. And then in the end, round it to the appropriate place. And that's just a nice way of keeping track of that. So what I'm going to say is that n cubed atoms implies the mass of n cubed atoms is equal to, in fact, 8.9 times 10 to the third kilograms. So if I divide the mass of n cubed atoms by the mass of one copper atom, I should get n cubed. Does that make sense to everyone? So we hypothesize that the 1 meter by 1 meter by 1 meter cube of copper is actually n cubed atoms. Okay. Now it could be n1 times n2 times n3 because the lattice structure is not necessarily perfectly square, but basically you'd still have a total number of atoms that's some number times some number times some number. The net effect is that 3 number is total, that product of 3 numbers is still the total, and maybe one's bigger than n, one's smaller than n, and the other one's exactly n. So it'd still come out to be about the same thing. So now what I'm going to do is I'm going to take 8.9 times 10 to the third, and I'm going to divide it by the 1.046 times 10 to the negative 25th. And that's going to give me, in fact, 8.508. Again, that's 2 extra sig figs than I actually have, times 10 to the 28th atoms. Okay. Now that means that n is equal to the cube root of that. So I'm going to take that number and raise it to the 1/3 power. And that gives me n is 4.39 or 4.40 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9th. So that's the total number of atoms. So the total, or excuse me, that's the total number of atoms in a row, because I said the rows were n by n by n. So basically that's how many is in a row. So if the row is 1 meter, then this is the number of atoms per meter. So I could actually write per meter like that. And now if I flip that over, what happens is 1 over n becomes, so I'm going to take the inverse of that. In other words, I want to raise it to the -1 power, and I'll get 2. And this is going to be the final answer. So I'm going to go ahead and round it. I'm going to get 2.3 times 10 to the -10th meters per atom. And that's really the separation between them. In other words, you'll have an atom, and then you'll have a distance of 2.3 times 10 to the -10th meters, and then you'll have the next atom, and then you'll have a distance of 2.3 times 10 to the -10th meters, and then you'll have the next atom. Now you can sort of think of that as if, okay, half of that distance is the radius of the atom, because you can sort of picture the atoms as if they're touching each other, or you can picture them as if they're little balls separated by a length of 10 to the -10th meters, and then it has nothing to do with the radius. But when you get from the solid state to the liquid state, it actually becomes more about the atoms sort of leaning against each other. So it might be better argued that, at least in the liquid state, the separation distance is their radius, so that the total, or excuse me, is twice their radius, so that the total separation distance is in fact equal to the diameter. So any questions on that? How I did that? There's not really a formula for it, but by analyzing the units and thinking clearly, you can still manage to come up with an answer. So does anybody have any questions on that one? Okay. So I'm going to do something else as well. Let's say, using this idea of atoms being discrete things, let's say that we're putting masses of carbon and masses of oxygen together. So example. So, oops. We feed carbon and oxygen into a machine, and we notice that when 135.5 kilograms of oxygen has been used, uh, 50.9 kilograms of carbon has also been used. Whoa. The question is, what compound is created? So we can assume it's only got carbon and oxygen. So it can be one carbon with one oxygen. It could be one carbon with two oxygens. It could be two carbons with one oxygen. It could be two carbons with two oxygens. There's all sorts of different scenarios. Of course, we'll eliminate stuff like two carbons and two oxygens, and three carbons and three oxygens. Or if we did, for instance, carbon dioxide, that'd be one carbon and two oxygens. Which would be the same thing as two carbons and four oxygens, or three carbons and six oxygens. So we can ignore those multiple things. But the main thing is the fact that atoms bond as numerically integer numbers, then we can actually figure out what this is. So if you actually knew at this point, which I'm sort of going on the assumption and pretending at least that you don't know how to convert to moles, if you could convert this to moles, it would be a much easier way to solve it. But what I'm going to do is I'm going to try to figure out exactly what's going on here and figure out specifically exactly what element is being used. So what I can do is I can take the mass of oxygen, say, and divide it by the mass of the carbon used. And what that's going to give me is 135.5 kilograms divided by 50.9 kilograms. And that gives me 2.662. Notice that's a pure number. The kilograms cancel out. So I know the ratio is 2.66 of mass of oxygen used to mass of carbon used. Now let's compare the ratio of the molecular weights of oxygen to carbon. So oxygen to carbon, if we look on the periodic table, oxygen is about 16.0. It's actually 15.9994, I think. Carbon, on the other hand, is 12.011. But in both cases, we can pretty much just use 2 sig figs and call it 16 divided by 12. So I'll do 16 divided by 12, and that gives me 4/3, or 1.333, so on and so forth. Okay, so what we want to do is figure out in what ratio of carbon to oxygen would you atoms would you have a mass ratio of 2.66 like we had here. Does that make sense to everyone? So let's do that. I'm going to say the mass of oxygen to carbon is 2.662. And that's also equal to, let's say, well, I don't want to do it that way necessarily. As you can tell, it's actually a lot easier by converting these masses to moles first, and then you can make some sense of it. So I'm actually sort of feeling out my way as I go. What I'm going to do is I am going to say that the mass of the oxygen divided by the mass of the carbon is actually equal to, let's say some N times the molecular weight of oxygen divided by some, let's say, Q times the molecular weight of carbon. In other words, we're assuming that there are capital N atoms of oxygen and lowercase q atoms of carbon. We know that MO over MC is in fact equal to 2.662, but we also know that this is equal to N over Q times MO over C, which is 1.333. Everybody see what I did there? Any questions on that? I'm going to turn the chat back on in case someone's talking to me. Okay, it didn't look like anybody is. That's good. Okay, so I've opened up the chat. So all I did was I replaced that part with that, because that's what that is up here. So I can now solve for N over Q and find out that N over Q is equal to 2.662 divided by 1.333. And if you take 2.662 divided by 1.333, you get about 1.997, which is really, really close to 2.0, which actually is 2.00. So what we see is that N, the number of oxygen molecules, or excuse me, number of oxygen atoms, is equal to 2 times Q, which is the number of carbon atoms. Okay, so we can now make the conclusion that the compound being made is CO2, which equals carbon dioxide, the wonderful greenhouse gas. Anybody have any questions about that? So that's something else we can do when we realize what these discrete atoms give us. Is there's a numerical ratio of atoms that's always got to be integers individually. So each atom can only be a integer number of atoms, in other words. So when you make up molecules, there's no 2.5 atoms of this compound, of this element, and 1.5 atoms of this element. It's always going to be integer multiples of atoms. And because of that, we can use this little analysis. Now, again, if you know how to convert the actual mass of 135.5 kilograms to to moles, then this would have been a lot easier. Okay, it's just that I haven't taught you that yet, so I'm trying to show you how to do it without. Now, something interesting that comes out of this is something that I teach in my conceptual physics class when I do teach that, and it's the importance of understanding the kinematics and the mass properties of reactions. So when you actually fill up your gas tank has, for instance, a bunch of carbons bonded like this. In other words, gasoline really.
Excuse me, Professor.
Yes.
I'm confused how you got CO2 from N equals 2Q.
Okay, so remember I told you that if we had 1 carbon and 1 oxygen, that would be the same thing as 2 carbons and 2 oxygens, and 3 carbons and 3 oxygens, and 4 carbons and 4 oxygens. Similarly, if we had 2 oxygens and 1 carbon, that would give the same ratio as 4 oxygens and 2 carbons, or 6 oxygens and 3 carbons. So basically, the smallest Q could be is 1. So when I put in 1 there, I get 2 for N, and Q equals 1, which is CO2. That's one way of thinking about it. Does that make sense?
No, it does not.
Okay. And there is, to be honest with you, it's not the cleanest argument either, because if you know about hydrogen peroxide, do y'all know what the formula for hydrogen peroxide is? It's like H2O2. Okay. So there's a scenario where you can actually have least common, or excuse me, a greatest common factor between the two. But what we're saying here is I'm not allowing any greatest common factors. So when I did that N over Q, if I divided that and got 3 halves, then that would be pretty straightforward, because I could say, well, Q would be 2 and N would be 3. But in this case, I got that the number of oxygen atoms has to be twice as many as the number of carbon atoms. Therefore, I conclude that it's either CO2 or C2O4 or C3O6 or C408. You see what I'm saying there?
The thing that confuses me is that 2Q, Q is the number of atoms of carbon. So
Right.
shouldn't it be like OC2 or C2O?
It could be, well, you could say the number of atoms of oxygen is 2x and the number of atoms of carbon is x, which I think is what you're trying to say. And that's absolutely right. It's just we know that carbon doesn't bond like that. It doesn't bond such that you'd have 3 carbons and 6 oxygens. We know of carbon dioxide, and that's pretty much it. Does that make sense?
All right.
Those are good. Those are very good questions, and you really got me at a point where I'm asked to try to explain a thing from chemistry that I don't know enough about to explain. But that's the crux of it. I wanted to write this a little clearer since the atoms was written out the side. So yeah, we definitely got that the ratio of the number of oxygen atoms to the number of carbon atoms is 2 to 1. Then it's just a matter of, yes, it could have been C2O4, or it could have been C3O6, or it could have been C408. We just happen to know that that's not a normal scenario, whereas carbon dioxide is. And actually, there might be, I'm not a chemist. I don't know. Maybe there is a C2O4, but I don't know of it. So I just call it carbon dioxide. Is that comfortable for a little bit comfortable?
Yes.
Okay. All right. So anyways, that's what that could be. Now, what I was talking about on this other part was I was trying to say that when you put gasoline in your car, essentially organic chemistry is about hydrocarbons, or carbon specifically, and all the things that it bonds with. And if you take oxygen, or if you take gasoline, for instance, it could be carbon and carbon and carbon like that. And then, of course, it would have a hydrogen here, 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 and a hydrogen here. And when you actually burn that gas, you break it up and out pops, hydrogens and carbons. So if you put out, for instance, let's assume the car's exhaust put out 1 kilogram of carbon. That carbon bonded with oxygen to make CO2. So how much CO2 was made? And I think what you see is the ratio of mass of CO2 to mass of carbon should be equal to, well, what we're going to do is we're going to take 135.5 kilograms and we're going to add to it 50.9 kilograms. And then we're going to divide that by the 50.9 kilograms. And when you do that, you get 135.5 plus 50.9. That's 186.4. And now I divide that by 50.9. And that gives me about 3.66 kilograms. So the important part that I'm trying to point out to you here is that if your car only puts out 1 kilogram of carbon, that's going to result in nearly 4 kilograms of carbon dioxide. And that's part of the problem with global warming, is specifically not only are we putting out carbon, we're putting out carbon, it's stealing oxygen from the atmosphere to make CO2. And in fact, that makes the net effect even bigger than what the car put out, because the car only put out 4 kilograms, but we ultimately resulted in, the car only put out 1 kilogram, and we ultimately got 3.66 kilograms out of CO2. Does that make sense? Any questions on that? All right, so that's just a little sidebar with regards to how chemistry works. It's the stoichiometry. Go ahead. Someone was going to ask something.
Yeah, sorry. I think I'm realizing what the guy was questioning earlier. Looking up at the thing, it would look like that. I guess N would be 1 for the atoms of oxygen versus 2 atoms for the carbon. So I'm confused. I know that the answer is going to be carbon dioxide, but looking at, I guess, the way that's written, I would intuitively put 1 oxygen, 2 carbons.
You got that a little backwards, but I think you're seeing right. You're just sort of making a little boo-boo with your algebra here, because N, the number of oxygen atoms, is equal to 2 times Q, the number of carbon atoms. So whatever carbon is, oxygen is going to be twice as much, just by N equals 2Q.
I see.
Yeah, there you go. It's the kind of mistake I make all the time. But yeah, it is the same thing. But because of that, we don't know. I mean, to be honest with you, it could be C2O4. And it could be C306 or C408 or whatever. But I'm going to go with carbon dioxide. And if I ever look in the chemistry book and I see C2O4, I'm going to come write y'all a letter. Okay. Any questions now? I think we're in a pretty good spot on that. All right, so let's go a little further. And what I'm going to tell you is we did make the conclusion that as temperature increases, the separation between individual molecules is going to get larger and larger, or between individual atoms is going to get larger and larger. That's sort of the idea of the atomic theory of matter. And one way we might wish to write that is we might say that the change in length, say, of a steel rod or a copper rod or an iron rod, which is the same thing as steel, or aluminum rod, we would probably suspect that if you increase the temperature of a rod, it's going to get longer. And for instance, if I increase the temperature of a 1 inch long rod, I suspect that that rod's going to get longer, but not by much. Whereas if I do the same thing, take it from the same initial temperature to the same final temperature of a 1 mile long rod, I think you'd see that the change in length would be quite a bit larger, wouldn't it? Do y'all agree with that, or do you see my reasoning there? Anybody want to try to fight me on that or anything? Okay, so I'm going to go on the assumption that that makes sense to you. One way you can think about it is the smallest rod you could make is 2 atoms, right? And if you increase the temperature, then that's just going to make the separation between the 2 atoms get larger. But if you now up that to 3 atoms, then the same bond between the first and the second atom is going to increase by the same length it did before. But now you've got the second bond doing the same thing, so it's like twice as long. The reason why I'm saying all this is to let you realize that the change in length of the rod is actually directly proportional to the original length of the rod. Now, I think you'd also suspect that if the change in temperature is 1 degree Celsius or 1 Celsius degree, that's actually what you're supposed to say when you do a difference in temperatures. You say Celsius degrees instead of degrees Celsius. I don't think you'd expect a very large change in the length. But if I did instead a 10 degree or 10 Celsius degree change in temperature, I would suspect that the length would be considered, the change in length would be considerably larger. So in fact, you'd also say that the change in length is proportional to delta T. Does everybody sort of agree with that reasoning? Anybody have any problems with that reasoning? All right, so if we go on the assumption that y'all are believing me, that y'all believe this charlatan, Mr. Younger, with his Pusheen cat shirt, then we can make this into an equality if we just do something else. Okay, normally what you'd have to do is just put a constant in here, but we're forgetting something. We're forgetting that, for instance, copper probably behaves slightly differently than aluminum, and they both probably behave differently than does steel, and so on and so forth. So what we could do is add a constant and then also add a parameter that's indicative of the individual material. And then it's just a matter of doing experiments and figure out what that constant is for the particular material. Now, we could just absorb that extra constant and just call the whole thing this new constant, and that's what we're going to do. So what I'm going to do is I'm going to say, let's make this proportionality, which is what that little fish symbol, that thing that looks like a little fish with no back tail, okay, that just means proportional. So now I'm going to make that into an equals by writing delta L is equal to L0 times alpha delta T. And that's just unfortunate that that alpha looks just like the little fish. This is called the linear coefficient of expansion. And it's a property of the material. So it's one of those things you could use as a chemist if you're trying to identify a substance. You could take a certain length of it, cut it down to a perfect cylinder, change the temperature, see how much it changes, find out what that alpha is, and then look in a CRC, that same book I mentioned earlier, and say, oh, well, this could be either copper or lead, say. And then you go back and say, well, let's check the density. Well, the density is 8.9, whereas the density of lead is like 9.2 or something like that. So you reach the conclusion that it's copper. And that's what we can do. So this, in fact, is one of the equations, but it's not the equation we normally use. But I like starting with it because that's a good heuristic or a good logical argument that can be made to create that actual equation. Now, if I realize that delta L is actually L minus L0, then I can change this all up and say that L minus L0 is equal to L0 alpha delta T. Or I could say that L is equal to L0 times 1 plus alpha T minus T0, because that's what delta T is. Okay, so that is in fact yet another version, and that's the version that we normally use. So I'm going to write down here and show you that this is alpha as well. So let's try an example. Okay, an example would be a 300-meter slab of concrete. Whoa, I spelled concrete really funny there. I'm going to take away all of that. And notice concrete is the substance. Cement is what glues it together. But a 300-meter long slab of concrete is used as a driving surface on a suspension bridge. And is 300 meters long at 20.0 degrees Celsius. How much will its length change when T equals 40.0 degrees Celsius? So I can call that part A, say. And then part B, how about when T is equal to negative 32.0 degrees Celsius? That's really, really cold. Okay. So we're talking like North Pole cold, okay, or at least Wisconsin cold or something like that. So let's do that. I'm going to start off with part A. I'm going to write the solution in black this time. Now, what I know is and this is a wonderful thing, for concrete and steel, they're both about the same. So alpha concrete is approximately equal to 12 times 10 to the negative 6 Celsius degrees reciprocal Celsius degrees. So I can actually use that now, and I'm going to say part A, delta L, actually, no, I'll say the new length. I'll say L is equal to L0 times 1 plus alpha T minus T0. So in this case, I'm going to say 300 meters times 1 plus 12 times 10 to the negative 6 reciprocal Celsius degrees times 40.0 degrees Celsius minus 20.0 degrees Celsius. Okay. And just quickly doing that math, I'm going to get 20 times 1, 2 e to the negative 6, which is 0.0024, and then I'm going to add that to 1, and then I'm going to multiply that by 300, and that gives me 300.072 meters. Implies delta L is like 7.2 centimeters for part A. 7.2 centimeters is pretty good. Remember, centimeters 2.54, or 1 inch is 2.54 centimeters. So if you divided that by 2.54, you'd get nearly 3 inches. That's a pretty significant thing. You could run through a 3-inch hole with a car. I wouldn't necessarily recommend it, but you could. But let's check B. So with B, I'm going to get L is equal to 300 meters again. And then it's going to be times 1 plus 12 times 10 to the negative 6 Celsius degree reciprocals, times, now I'm going to do negative 30.0 degrees Celsius minus 20.0 degrees Celsius, which gives me a freaking 50, a negative 50. So I'm going to say negative 50 times 1, 2 e to the negative 6. That gives me 0.0006 negative.
Isn't it supposed to be negative 32 degrees Celsius?
I think it is negative 32. Nice catch. You could tell I actually worked the problem before and I had done just plain 30. That's probably what I was doing, but thank you for that. So yeah, that should definitely not be 50. That should be 52. So let's do 52 times 1, 2 e to the negative 6. Shrink that back down. That gives me 0.000624 negative. So I add 1 to that, and that gives me, oh crap, negative 6.24 e to the negative 4 plus 1. Now that gives me 300 meters times 0.999376, which equals 299.8128 meters. So if I tell the difference between that and 300, that means delta L is actually equal to 18.72 centimeters. It's actually a negative, by the way, which is actually about 7.37 inches. So that's a really, really big change. So that's a big engineering feat that you got to deal with when you're designing these things. If they're going to go through ranges of temperatures, they can be really huge ranges of temperature. And that's a net swing of going up by 7.2 centimeters and then going down by 18.7 centimeters. So we're talking a total of what, 25.9 centimeters? So that's a total swing of 25.9 centimeters, which if I divide that by 2.54, I get 10.2 inches. So imagine 10.2 inches difference. If you just have, for instance, that end of that slab sticking on a rail that holds it, it could literally shrink enough that it would just fall down, which from what I've experienced, most bridge drivers do not enjoy the bridge that you're driving on to fall out from under you. So it probably would not be a good engineering design. Am I right? All right. Well, we've already reached our time. I am going to probably post a couple videos this weekend of some more problems. Of course, you can look at my YouTube channel as well. We're probably still going to have to do a little bit more from chapter 17 on Tuesday, but I think I'm jumping into chapter 18. But I am going to move your homework back so that your homework will not be due Monday at 11:59 p.m. I'm going to go ahead and move it back to Wednesday at 11:59 p.m. because I just didn't get far enough in this first chapter. Okay. Anybody have any questions? Well, you guys are all free to go, and I'm going to wait for the last person to leave in case anybody has any questions. Thank you all for coming. Start on your homework. Do not wait to the last minute. Go ahead and start on it. You can probably do at least half of the homework problems already. Really all I'm missing at this point is I was going to do one where you fill up a gas tank with, say 80 liters of gas at, 20 degrees Celsius, and then see how much gas overflows when it becomes 40 degrees Celsius. I wasn't going to work the problem where you calculate the force of, say, that 300-meter concrete slab expanding directly against another slab. That's the problem worked in your book. But I'm not going to require you guys to know that. But it is interesting. It's a cool engineering problem to do, and it's neat to find that force. But I'm not going to require that of you. I'm just going into, after this, the ideal gas laws, specifically Boyle's law, then Charles's law, then Gay-Lussac's law, and then Dalton's law of partial pressure, and then putting it all together to make the ideal gas law, PV equals nRT. And I'll solve a couple problems with that. I will mention Van de Graaff and Clausius's equation of state, but I'm really not doing anything with it, and I'm not going to require you to do anything with it in your tests. So you guys are free to go. Feel free to ask me any questions, or go ahead and split so you can, actually, I guess you don't have to hit lab, right? Nobody has lab today, do they?
No, it's Tuesdays, or at least the one I'm in is Tuesdays.
Yeah, I think that's the only one. That's cool. Y'all have a good weekend and stay safe for me.
One quick question. Do you post all of these online?
I do. I usually post them the same night. Sometimes it has to wait till the next morning, but
Gotcha.
basically it converts right after I get offline. And when it's finished converting, I post it to my YouTube channel.
Gotcha. Okay, just look there.
You'll get an email when it's done.
Gotcha. Sounds good.
No problem. See you, Jake.
All right. Thank you. Have a good one.
How about you, Yatal? Do you have a question, or Tony?
Hey, Professor, it's Tony Posada.
Hey, Tony.
I think I sent you an email. I'm having issues logging into the master in physics. It keeps asking me for a course ID, and I cannot find it anywhere in the syllabus.
Okay. Yes, you do not want to use that. So it sounds like you're trying to go to my lab and mastering from the internet, and you don't want to do that, because if you manage to make it, then I'll never be able to see your grades, and that's kind of problematic. What I've done is what's called a deep integration. So what you want to do is go into Canvas and then click on chapter 17 homework. And at that point, it'll ask you to insert your access code, or take a 2-week free trial, or purchase an access code. If you have any problems, if it doesn't give you an option of entering your username and password from the 241 class, if it doesn't give you that, then just take your 2 weeks free pass and then contact my lab and mastering's technical support and tell them, hey, I've already got an account. Why is it not giving me the option to use that account? But it's supposed to give you an option to just log in with your old username and password.
It does. When I log in, it gives me an option to, if I go to the Canvas, I go to if you go to syllabus, then there's like a master in physics. I click on that, it gives me the option to buy. But when I click on it, it just says an error, and it just it won't let me do anything. And then, so I change from Safari to Chrome. And then when I go in there, it keeps asking me for the course ID.
Yeah. Okay.
So,
well, yeah,
I'll try for the homework.
Even if you can manage to find the course ID, which can be done, you don't want to, because in order for it to use the course ID, it's going off the Canvas, it's going onto the web, and I won't see it through Canvas. So what you probably need to do is contact technical support and tell them what you're trying to do. But instead of going to the My Lab and mastering, try going straight to the homework assignment and see if it'll let you put your username and password in that you used when you took 241. I assume you took 241 fairly recently?
It was about 2 years ago.
Oh, okay. So you're going to have to buy a new one anyways.
Yes.
Okay. So just do purchase the access code there. It'll actually be cheaper anyways than doing it through the bookstore. So yeah, just purchase it there. But if you don't have the money right now, go ahead and do the 2-week free trial. And then at the end of 2 weeks, you can pay.
Okay, I'll try from the homework then.
All right. Thanks, Tony.
I appreciate it. Thank you.
You too. Have a good one.